Simultaneous localization and mapping, SLAM, is a pivotal task in 3D computer vision, with the goal of estimating the position and orientation of a sensor. While concurrently building a map of the surrounding scene, the system takes in sequential frames captured by an RGB-D camera, which includes both color and depth information. The camera's position and orientation, pose, are continuously estimated relative to the environment based on the incoming RGB-D data. As new observations from the RGB-D stream are received, they are integrated into the existing map. This process allows the map to grow and evolve. Recently, the accuracy of 3D representation has qualitatively improved by using neural implicit representation. Essentially, neural radiance field, NeRF, is an emerging technique based on implicit neural representation, in combination with geometric rendering. It achieves state-of-the-art novel view synthesis results. It employs a multilayer perceptron as its implicit neural representation to map a 3D point to density and color via differentiable volume rendering. Various NeRF variants have emerged since, featuring unique representations such as grid and triplane, or focusing on mapping the 3D point to different geometric properties, such as the surface rather than density, while developing corresponding geometric rendering strategies. NeRF effectively models the intrinsic structure of a specific scene, capturing its geometry in a compact yet expressive manner that aligns closely with observed locations. As a result, it inherently incorporates the corresponding observation positions. This feature facilitates the deduction of camera poses directly from the trained NeRF, thereby enabling NeRF to regress pose while constructing the surrounding environment, that is, SLAM. Several challenges exist in pushing the NeRF-enhanced SLAM systems into the next stage. The first challenge is the absence of unified benchmark framework. There is no standardized framework for comparing NeRFs in RGB-D SLAM systems, making it difficult to track progress introduced by NeRFs due to varied SLAM system strategies such as keyframe selection. The second challenge is the lack of assessment of NeRF component variations. There is no systematic evaluation of the traits of implicit neural representation and geometric rendering function combinations in SLAM systems under different scenarios, neglecting the SLAM performance variation due to the introduction of different variants, such as MLP and triplane, which could further differ on a scene basis. Therefore, we propose to benchmark commonly used NeRF and its component variants under a unified SLAM framework. Implicit neural representation, in combination with geometric rendering, has recently been employed in real-time dense RGB-D SLAM. Despite active research endeavors being made, there lacks a unified protocol for fair evaluation, impeding the evolution of this area. In this work, we established, to our knowledge, the first open-source benchmark framework to evaluate the performance of a wide spectrum of commonly used implicit neural representations and geometric rendering for mapping and localization, to understand to which extent different components affect system behavior. We observed that NeRF is highly sensitive to the style of the trajectory. Notably, some implicit representations, while beneficial for pose estimation, often require the introduction of excessive spatial redundancy to achieve this when the trajectory loop is not closed, which is not conducive to applying NeRF in real SLAM scenarios. Therefore, in this study, we set up two scenarios based on two typical SLAM trajectories and established two corresponding leaderboards. We refer to the loop closure scenario as the lab scenario, while the scenario with a more arbitrary trajectory is called the practical scenario. The entire benchmarking framework starts from these two scenarios and is measured by 8 metrics. For the evaluated targets, SLAM methods A, B, and C that we collected, we proposed an RGB-D SLAM framework that unifies the common modules of these target methods, such as sampling, keyframes, and training. Based on this framework, we measured the impact of our different NERF components on the SLAM system. Finally, based on our observations on leaderboards, we provided insights and developed a better representation solution, a hybrid representation method. We firstly observed the impact of various combinations of NERF components on SLAM system performance under a lab scenario. The resulting leaderboard shows that the dense grid representation excels. It achieves overall 6 top and 3 second place rankings. This is followed by sparse encoding, which secures 2 top spots and 4 second place, with the triplane claiming 1 second place spot. In our framework, the dense grid representation achieved better results with fewer parameters and resolution levels compared to the previous use of the same representation, demonstrating the effectiveness of our unified SLAM framework. However, the observations in the lab scenario are not consistent with those in the practical scenario. We found that the triplane representation seems to have a higher advantage in terms of scene completeness and trajectory accuracy, while grid-based methods still hold an advantage in aggregation and texture representation. This motivated us to propose a hybrid encoding that combines grid-based representation with triplane representation. This encoding method effectively compensates for the respective shortcomings, forming a new state-of-the-art. Our benchmark study strictly controls feature dimensions and spatial resolution. However, optimal performance in such controlled comparisons may not always align with real-world application priorities. For example, if applying triplane encoding with a hash grid rather than a dense grid, a minor compromise in accuracy, for instance, a 1 mm decrease in trajectory estimation accuracy, can lead to substantial gains in efficiency, such as an 87.93% reduction in memory usage. Hence, in practical scenarios, a hybrid approach combining triplane and hash encodings might be a preferable alternative to the triplane and dense grid combination. Most importantly, hybrid encoding of triplane and hash GERD notably reduces artifacts compared to triplane and dense GERD alternatives, as well as the similar strategy proposed by CoSLAM. Our evaluations show that dense grids, along with their hybrid encoding with triplane, excel in implicit scene encoding across 2 prominent leaderboards. To evolve these techniques for NERF-based mapping, enhancements in computational and memory efficiency are necessary. Dense grids exhibit cubic scaling with resolution, while octrees show logarithmic scaling in sparse environments. Therefore, we propose an explicit hybrid encoding to substitute the coarse-level feature grid with an octree structure and simplify the encoding process by using a single-level dense grid. Compared to the dense representation in NICE SLAM, we employ 16 times less implicit dimensionality and 3 times less copy of different resolution grids, while achieving high-fidelity online map updating. Explicit hybrid encoding achieves map updating at approximately 1 Hz, compared to around 0.25 Hz for NICE SLAM.